I'd like to introduce our next speaker, Dr. Tamer Kahveci, right? I hope I pronounced your last name correct, Kahveci, from University of Florida. And Tamer is associate chair of the Department of Computer Science there. And Tamer has a long list of contribution to the bioinformatics community. I will not list there, so please read his bio posted in the website. And we are fortunate to have Tamer here to give a talk. And Tamer, so it's all yours.
Thank you. Thank you so much for the kind introduction. Share my screen. Is my screen visible to everybody? I don't?
It is.
Okay, perfect. Right. Thank you and welcome to my talk. I'm going to be talking about the motif counting problem, which is a very fundamental problem in understanding how biological systems work. And particularly, I'm going to be focusing on how the evolution of biological networks influence the motif counting problem. I cannot see my own slides. Okay, as we all know, biological networks describe how different molecules interact with each other. And depending on the type of the molecules that interact and the kind of interactions that takes place between them, we categorize biological networks in several categories, such as metabolic networks or protein interaction networks. But usually we represent these biological networks, as you all know, using graphs. And the nodes in the graphs are typically going to be representing the molecules, and the interactions between them are going to be represented by edges between the nodes. Now, under this mathematical model, a motif is simply a small graph pattern such that this graph pattern appears in a given target network much more frequently than you would have expected in a randomly generated network of the same size. Of course, in order to talk about whether a motif appears so many times in a given network, the first thing that we need to mathematically define is how do we count a motif in a given network. In the literature, there are typically three different ways to count motifs. I'm going to call them F1, F2, and F3 measures. And I'm going to explain them very briefly on this toy example. So in my example here on the top, what you see is a motif pattern. And at the bottom is a small hypothetical network. Now let's start with the F1 measure. The F1 measure simply says that, hey, I want to find I'm only interested in the number of possible ways to place this motif on top of the target network. For example, I can place my motif on the network like this, or like that, or like that. So there are three different ways to do this placement. So the F1 measure says that my count is equal to 3. Now let's take this motif and make it slightly bigger by adding a new node and a new edge to the motif. Now, how many times does this motif appear in the target network? You can notice that there's only one copy over here. So the F1 measure goes down from 3 to 1. Now, at this point, you're possibly thinking that it's not surprising that the motif count went down because my motif actually got larger. So larger motif means more constraints, so the motif count is going to go down. But actually, that's not the reason why the motif count went down. To understand this better, let's just do the opposite and make our motif slightly smaller, this time by reducing a node and an edge. Now, let's see how many copies of this motif I can place on the target network. There's one copy here and another copy here. So my F1 measure is going to be equal to 2. And from this simple example, we observe that as we grow the size of the motif, the number of times that we can observe it according to the F1 measure sometimes goes up, sometimes goes down. So it's not monotonic. When this happens, we say that this measure does not have the downward closure property. And when the downward closure property is violated, it's really bad for a lot of problems, a lot of questions that you can ask on the biological networks, including all the prediction and the qualification, classification problems on biological systems. F2 and F3 measures deal with this problem by adding some constraint on the measure. So F2, for example, F2 measure says that I'm going to place my motif on the target network with the constraint that these placements do not share any common edges. So edges have to be independent of each other. So with this constraint, I can place a motif here and another copy over here. So 2 copies in total, and they do not have any common edges. And this is the largest number of placements that we can have on the target network. So my F2 measure is equal to 2. The F3 measure is more stringent. It says that not only the placements of the motifs should be independent in terms of the edges, but they should also be independent in terms of the nodes. So I'm not going to allow any overlaps between the nodes and edges. When you have this constraint, there's only one copy of the motif that I can place on the target network, and any other copy that you can place is going to be overlapping with this. So the F3 measure is going to be equal to 1. So when we put all these 3 measures together, we observe that the first one does not have the downward closure property, but F2 and F3 do have the downward closure properties. We can prove that mathematically. So I'm going to be focusing on the F2 and F3 measures in the rest of my talk. And particularly, I'm going to be focusing on the second one because there's like algorithmically very, very tiny difference between the F2 and F3 measures. But regardless of the measure that you pick over here, all these 3 motif counting techniques are NP complete, computationally very expensive. Now, those of you who do theory among you are going to hate me for saying this, but I'm going to say that F2 and F3 measures are going to be harder problems than the F1 measure because you have to solve not one NP complete problem, but 2 NP complete problems for each one of them. But at the end of the day, it's still NP complete. Now let's talk about a little bit about the evolution of the networks. The network topologies are not static entities. The network topologies change over a period of time. And these topological changes take place for many, many reasons, like stress conditions, like extreme heat, cold, oxidative stress, lactose stress, aging, or many other reasons. But regardless of what the reasons behind the evolution is, the network topology changes over a period of time. We mathematically represent this evolution of networks over a period of time as a sequence of events where each event is an edge insertion or an edge deletion to the network. Now, we can also consider this as node insertion, node deletion as well, but it's essentially the same thing when you take all the nodes in all the instances that you observe together, take their union, and whenever that node is not observed in a certain state, it just becomes an isolated node with no edges. So I'm going to represent it as a sequence of edge insertions and deletions. And mathematically, I'm going to represent it using a tuple. The first entry in this tuple, G0, is the topology of the initial network with all the nodes and edges. The second entry is a sequence of edges where each edge represents the edge that gets inserted or deleted from the previous state. So if you have that edge in the previous state, then you remove it. If you don't have it, then you insert it. So this way I can represent a sequence of n dynamic network states using this tuple. Under this definition, I redefine the motif counting problem as follows. So given a motif topology and such an evolving network with n different network states, my problem now is to find the number of times this motif is observed in each of these instances of the evolving network. So if there are 1,000 states, I want to find the motif count in each and every one of those 1,000 states of the network. Now, I just said in the previous slide that this is a NP-complete problem. It's computationally intensive for just one network which means that I definitely do not want to compute this over and over again for thousands and thousands of network topologies. And what I'm going to describe is a strategy to do this incrementally by just using the current motif count plus the observed changes from one state to the next state of the network. Just a second. All right. So to explain this concept, I need to first explain how we calculate the motif count, the F2 measure, in a static network first, which is the initial state of the network. I'm going to explain this, our algorithm, which is an algorithm that works in 2 steps. I'm going to explain it on this small example. So here we have a small hypothetical motif, and here we have a target network with 6 nodes and 10 edges. In the first step of our algorithm, what we do first is we find all possible placements of the motif on the target network, regardless of their position, regardless of whether they overlap or not. I ignore all the constraints and I find them. For example, one possible placement is edges 1, 2, and 3. So I find this and I keep that information. And as I do this, I start creating a new graph, and I'm going to call this an overlap graph. In the overlap graph, each node corresponds to one possible placement of the motif on the target network. So for example, this one corresponds to H1, that is edge 1, 2, and 3. So I repeat this, I find the next placement of the motif, which is 3, 4, 5. So I create a node for that. And then I insert an edge between these 2 nodes, meaning that these 2 placements of the motifs have a common edge. They are overlapping with each other. In this case, it's the 3rd edge that is common to both of the embeddings. So just like that, I continue finding new embeddings and grow my overlap graph with new nodes and new edges. And this is what I have at the end. Next, I need to select a subset of these placements of the motifs such that everything that I selected is independent of each other. They do not have common edges, plus it's as large as possible. So to do that, I make the following observation. I say that, hey, if I select any node, any placement from here, I cannot select any other node that has an edge with that node. So every edge for a given particular node is a constraint which prevents me picking from something else. So from this observation, I make a greedy decision to pick the node with the smallest degree, which is either H1 or H5 in this example. So I randomly pick one of them and put it in the result set. Now notice that H1 is connected to H2, which means that I cannot select H2 anymore. So I remove this from the overlap graph and I repeat the same process. Now my options are 3 and 5. So I pick one of them, put it in the result set. 3 is connected to 4, so get rid of 4. Now I have only one node left, so include it in the result set. And there you go, we have our solution, which is 1, 3, and 5. I can place my motif in 3 different places without any overlap. So that is the algorithm for the static network. Now, how do we extend this for dynamic networks? To do that, I'm going to need an auxiliary data set. In this auxiliary data structure, what I have is a list for each edge. In this list for each edge, I maintain the list of embeddings which contain that particular edge. For example, let's focus on the 3rd edge. The 3rd edge is contained in the 1st placement and the 2nd placement, H1 and H2. So the list contains H1 and H2 over here. Now let's start dealing with the evolution of the network. First, I'm going to look at what happens when we remove an edge from the target network. So let's remove an edge. In this case, it's going to be edge number 7. Now, when we remove an edge, what happens is that any motif instance in which this edge that I have removed participates is going to disappear from my solution set, which is 3 and 4. So these 2 are gone. Now remember that my optimal solution at this previous state was 1, 3, and 5. Just keep that in mind. So I remove 3 and 4. I go and update my auxiliary data structure, remove 3 and 4 wherever they appear. And then, because 3 is a part of the solution, I need to reduce my motif count by 1. But maybe I don't need to reduce the motif count by 1 because H3, when it was in the solution set, it was adding a constraint that I cannot add any of its neighbors. So maybe one of its neighbors, which could not be in the result set before, now can be in the result set. So to find it out, I look at this. It says that if there's a solution that can be included in the result, then it should contain 4 or 6. So I look at 6. Now 6 is empty, so I cannot include anything from here. Then I look at 4. 2 is available. So maybe I can include 2, but can I include it? Now H2 doesn't conflict with 3 anymore, but it still conflicts with 1. So I cannot include H2 anymore, H2. So my motif count goes down by 1. Now let's see what happens when we insert an edge. So I'm gonna insert an edge and call it edge number 11 over here. Now when I insert an edge, what can happen is that I may produce a new instance of the motif. Of course, to find out if we generated a new instance of the motif, we don't want to solve the motif counting problem from scratch again. That's too expensive. I want to do it quickly. So to do that quickly, I first look at my motif topology. What is the diameter of this motif? The diameter is the length between the farthest away pair of nodes. So the distance between these two nodes is 1, these two nodes is 1, 1. So the largest one is 1. So it means that my diameter is equal to 1. So what does it mean? It means that if there's a new solution, it has to be within a distance of 1 from the newly inserted node. So if there's a new solution, it has to be a combination of the red and the green nodes. So I only restrict myself to these colorful edges, and I observe that there is actually one new instance of the motif, which is 5, 9, and 11. So I'm going to call it H6. I generate it, I insert it in the overlap graph. I update my auxiliary data structure with the new list. Now 6 appears in, also contains edges 5 and 9. So I need to update those two as well. And then I have to check, hey, is this new motif placement, is it possible to include it in the result set? So remember that my solution was 1 and 5. So I need to check if this new embedding is overlapping with any one of them. So there's an edge here. So it means that unfortunately I cannot include that. So my motif count doesn't change. So this is the algorithm in a nutshell. So next I'm going to show you the evaluation of this algorithm. So we evaluated our algorithm on synthetic and real data sets. For synthetic data set, we generated random networks using 3 different random network models. Erdős-Rényi, Watt-Strogatz, and Barabasi-Albert models. We generated networks from 1,000 to 5,000 nodes with average degrees from 10 to 20. For each one of these combinations of parameters, we generated 10 random networks. And for each of those random networks, we created a sequence of 1,000 evolutionary steps by just doing random shuffling of edges using the degree preserved shuffling like this. For the real data set, we use a data set that we generated in one of our previous papers. So this is a data set from human embryonic stem cell and its evolution into different tissues. And we particularly focus on pancreas and liver. So there are 2 pathways of evolution from stem cell to pancreas, stem cell to liver in our data set. The size of this data set is roughly like 2,000 nodes, 14,000 edges. And one of the pathways contains about more than 3,000 network edit operations, edge insertion and deletions. And the other pathway contains more than 2,000 edge insertion and removals. These are the motifs that we tested our algorithm on. So we use these motifs because in another paper before we have proved that this is the minimal subset of motifs which can be used to produce any other motif of any topology of larger size. So there is no other subset which is smaller than this, whose combination can produce every possible topology. So in this experiment, we measured the running time. What you see is the red line, horizontal line over here is the running time of calculating the motif count only for the initial state of the network. So if it was a static network with only the initial state of the network, this is the running time. The blue horizontal line shows you the total time to calculate the motif count only for two states of the network, which is the initial state and the final state of the network after 1000 edit operations. What you see in between this diagonal line is the running time of our algorithm for calculating the motif count at each and every state of the network for 1000 consecutive network edit operations. So what we see here is that in all these three random network models, Erdős-Rényi, Watt-Strogatz, and Barabasi-Albert models, we see that at the beginning, we pay more cost than calculating the motif count just once, because we need to maintain all this additional data structure, auxiliary data structures. But then once we pay that little cost, we can incrementally update the motif count with such a negligible cost that we can do this operation 1000 times, and still it's not going to be as much as doing it only twice. So the cost here you see at Barabasi-Albert is slightly more, actually relative to the red and blue line, it's more than the Erdős-Rényi and Watt-Strogatz methods. And this is happening because in the Barabasi-Albert model, the nodes are going to be well connected to each other. There's going to be some hubs. As a result of that, there's going to be a lot more instances of motifs in the target network of the same size under this model than the other two models. But nevertheless, we can calculate the motif count for 1000 steps and still spend less time than calculating it only twice. Next, I'm going to show you the accuracy of our method at the most disadvantageous stage of our method, which is the final stage. So we make 1000 decisions, and some of them are heuristic decisions. How bad is our result after 1000, the network has evolved at 1000 steps? How much does it deviate from the optimal result, which calculates it from scratch at the final stage? And we report the results for different number of nodes, different network topologies, and 4 different motifs that I showed you before. In all of them, what we observe here is that our method has an accuracy of, this is the lowest point, 96%, up to about 100%, so very high accuracies. And we also observe that for larger networks, our accuracy seems to be doing better. This is the accuracy results for different network densities, degree from 10, 15, and 20, the average number of edges per node. Again, the accuracies are very high. So it's about 96% at the lowest point and about 100% at the highest point. It ranges between the two. And with increased network density, our accuracy seems to be getting better, especially for the Barabasi-Albert and Watt-Strogatz methods. Next is the real data set. These are the 2 pathways, stem cell to pancreas, stem cell to liver evolution. Now, I want you to notice that the number of dynamic steps here is much more than the number of dynamic steps that we had for the synthetic experiments. It's more than 3000 here, more than 2000 over here. And you're going to see that our results for the real data set are actually better than our results for the synthetically generated data for any of the 3 random network models. So although we calculate the motif for so many different steps, we are still below the total cost for just 2 static network motif counting operations. This is our accuracy for the 2 pathways for the 4 different motifs on the real data. Again, the results that we are observing are better than what we were observing for the synthetic data. Our accuracy at best is somewhere between 97, 98% accuracy and around 99% accuracy. So in conclusion, we show that the motif counting problem, which is a very difficult problem, NP-complete problem to do only for even a static network, it can be solved incrementally for evolving networks with very, very negligible cost and very high accuracy. Another observation that we have is that the bias degree distributions, especially those that we observe in real networks, are actually benefiting the algorithm that we have. So we do better for those kind of networks than the synthetically generated networks. So these are my collaborators, my students, Kingshuk, Mahmoudou, Christina is a faculty in our department. And I'd like to thank you all. You can take questions.
Thanks, Tamer, for the great talk. We are at the time of a break, but there are two short questions. The first one, the F2 and F3 measures of motif counting are mathematically advantageous, but are there advantages for biological interpretation?
Mm-hmm. That's a very good question. So what we showed in different papers, several papers, is that the independent motif embeddings are going to show you the possible functions, the possible number of times that the ability of the system to function. So what I mean by that is the following. I guess I need to go back to the motif topology. Okay, let's go back to this example that we have over here. Okay, so what I mean is the following. Assume that this is a system with a limited resource. So these are gene products, and you have a limited product. So when the motifs are representing the functional units, for example, feed forward loops or feed backward loops, so whatever the underlying function is. So the purpose of making them edge independent or node independent is that we consider these as limited resources. So once you consume a certain resource, the next one should be independent of that because those products have been functioning in the process through a different combination of the nodes. So the more copies of that shape that you have, the more of that topological function that you can serve in the underlying system. So it gives you the set of the tasks that can be carried out independently in the underlying biological system. While the other one shows you not the independent one, the F1 measure shows you not the independent one, but the number of alternative ways to do it at different times. So I'm not saying that F1 measure or F2 or F3 measure is biologically, one of them is bad, the other one is good. They all have their meanings, but they have their own meanings. They mean different things. The way that I perceive the F2 and F3 measures is to understand how the functions are performed with limited resources. F1 measure, I understand it as how the functions are performed with unlimited resources. I don't know if that answer was clear.
Yeah. Tamer, so thanks. The second, maybe very short. How does this approach extend to graphs with directional edge?
It is the same algorithm. I mean, essentially, if you go over so there's really no difference between the directed and undirected ones. The only reason that I'm sticking to the directed ones is because of the kind of networks that we tested on, plus the motifs. So none of these steps in the algorithm change for directed or undirected networks. So we use undirected networks in this work only for practical reasons.
Okay.
I cannot think of anything that will change between directed and undirected.
Okay. Tamer, thanks. Thanks again for your talk.